Welcome to this explainer. Today we are taking a look at a piece of celestial machinery that, let's be honest, we completely take for granted. I'm talking about the luminescence of the full lunar phase. We're going to break down the specific geometry, the behavior of the light, and the actual mechanics of why this phenomenon works exactly the way it does. It's going to be a fun one, so let's get right into it. So, think about the night sky for just a second. Have you ever wondered what exactly creates the face on the moon? You know, you tilt your head back, look at that bright glowing orb, and there's that distinct face staring right back at you. Well, to really understand what's going on there, we have to connect the macro scale of orbital mechanics all the way down to the physical properties of the lunar surface itself. Okay, let's dive into this. A full moon basically comes down to a very precise cosmic alignment. It occurs when the moon is right on the opposite side of Earth from the sun, making the fully illuminated face completely visible from our perspective here on Earth. Astronomers actually call this alignment syzygy. Because of this syzygy, we get to see the whole face lit up. It perfectly marks the exact midpoint of the lunar cycle, which is roughly 2 weeks right after a new moon. And that specific geometry results in one crucial, absolute number, 100%. Because we're sitting right between the sun and the moon, the near side of the moon is just bathed in direct sunlight. Now sure, true 100% illumination, like without any microshadows hiding in the craters, only technically happens right before a lunar eclipse. But from our earthly vantage point, during a standard full moon, it really does reach its maximum possible reflection. It's literally a visual confirmation of our exact placement in the solar system. Because of this alignment, the full moon actually operates on this perfectly synchronized schedule. It's like perfect cosmic clockwork. Just as the sun sets in the west, the moon is simultaneously rising in the east. And why is that? Well, it's because the Earth is rotating exactly between these two massive bodies, making the moon act as this perfect celestial counterpart to the sun in our sky. It reaches its highest point right around midnight and then finally sets in the west exactly as the sun rises again. It basically stands sentry for the exact duration of the night. And this brilliantly illustrates exactly what we're looking at when all that light hits the surface. We're actually seeing a really stark contrast between two distinct physical surface features. So on one side, we have the darker Maria, right? These are ancient basaltic volcanic plains, or lunar seas, and that basalt just physically absorbs more light. Then, contrasting those, we have the lighter highlands. That's the older, heavily cratered crust that actively reflects a ton more solar energy. So it's actually the contrast between that light-absorbing basalt and the light-reflecting crust that totally tricks our brains into seeing that famous face of the moon. Now that perfect timeline and that near-perfect reflection, it kind of begs a really fascinating question. If the sun, the earth, and the moon are perfectly aligned, if they are perfectly aligned in syzygy, then why isn't there an eclipse every single month, right? Shouldn't the Earth's massive shadow just totally block out that sunlight every time we hit this monthly midpoint? Well, the answer actually comes down to three-dimensional geometry. You see, the moon's orbit around the Earth isn't perfectly flat. It's actually slightly inclined relative to Earth's orbit. It has this subtle tilt of about 5 degrees. Because of that 5-degree tilt, the full moon usually passes just a little bit above or a little bit below the Earth's massive shadow. So it's only when that specific inclination intersects perfectly with our orbital plane that we actually get a full-blown lunar eclipse. Now, what's really interesting about this slide is, despite how incredibly bright the moon looks to us in the night sky, consider this number, 1/400,000th. The brightness of a full moon is only a tiny, tiny fraction of the sun's energy. And a big reason it's actually so dim is that the moon's surface has a very low albedo, or reflectivity. To put that into perspective, its reflectivity is roughly similar to worn asphalt. Crazy, right? Yet even bouncing off what is essentially just dark gray rock at a mere fraction of the sun's power, it still noticeably illuminates our entire landscape. And, we really shouldn't overlook the practical impact of all that reflected light. Imagine a world before artificial lighting. This was literally our guiding nightlight. It noticeably illuminates landscapes. Think about the harvest moon, for example, which specifically provided critical light for pre-electricity nighttime activities, allowing farmers to continue gathering crops way late into the autumn nights. And beyond just utility, it sparked global cultural celebrations and mythologies. The reliable cycle of this glowing sphere actually anchored ancient timekeeping. Entire civilizations structured their agricultural and religious calendars entirely around these lunar phases. So as we wrap up this explainer, I want to leave you with this final thought. Next time you look up at night, what will you see in the glowing face of the moon? Are you going to see just a dark rock with low albedo? Or are you going to see the absolute perfection of cosmic counterbalance? Whether it's that subtle 5-degree tilt of its orbit or just the way it reliably anchored ancient calendars for our ancestors, the mechanics behind this whole shebang are absolutely fascinating. So keep looking up, keep asking those questions, and definitely keep wondering.